We had in the 2016 model, for instance, regardless of what other errors might have come in during sampling on that, we had models that were predicting a Clinton win by about 9 to 1 odds. And yet when they ran those exact same models through, which are much more difficult when you look at individual states, every state has a chance to, win or lose by so much. And these are all have to be shuffled together with individual probabilities. And we use approximations to make that easier. We don't have to do that with quantum computing. We used a learning model called a Boltzmann machine, which we probably should say for another occasion. And that one predicted using the exact same data and the same general trends actually showed Trump more likely to win that election by about 2 to 1 in some cases, but certainly not 10 to 1 against. And so this is an example. You can imagine how many other things we can use this for in terms of very parallel cases. But with the current US system, 50 states plus DC, each one of those, wins on its own. You have to pull each of those places individually. And so you can only get a very small sample from that. And trying to add those all together in the various combinations and permutations becomes very difficult to do on a classic computer. There are just too many scenarios. And so we approximate. The biggest thing about a quantum computer, and you were saying earlier about parallel processing, it's not running a bunch of processes simultaneously. It's running all of the processes simultaneously. Every single option that could be put in that is simultaneously happening. And what we do is try to remove all the ones that we can't, that we don't want to see, so that we only get the actual desired one that comes through to us when we look at it.